Next, oil under pressure compresses the layers of paper insulation and is forced into any voids that may have formed between the layers. Due to the elimination of voids, oil filled cables can be used for higher voltages, the range being from 66 kV to 230 kV. Oil filled cables are of three types: single core conductor channel, single core sheath channel, three core filter space channels. These are the oil duct, this is the conductor, this is serving layer, this is bedding layer, this is lead sheath, this is paper insulations. Figure shows constant detail of a single core conductor channel oil filled cable. The oil channel is formed at the center by standing the conductor wire around a hollow cylindrical steel spiral tape. The oil under pressure is supplied to the channel by means of external reservoir. Figure shows the constant detail of a single core external reservoirs. As this channel is made of spiral steel tape, it allows the oil to percolate between copper strands to be wrapped insulations. The oil pressure compresses the layers of paper insulation and prevents the possibility of void formations. The system is to be designed that when the oil gets expanded due to the increase in cable temperature, the extra oil collects in the reservoir. However, when the cable temperature falls during light load conditions, the oil from the reservoir flows to the channels. The disadvantage of this type of cable is that the channel is at the middle of the cable and is at a full voltage with respect to earth, so that a very complicated system joints is necessary. Figure shows the constant detail of a single core sheath channel oil filled cables. In this type of cable, the conductor is solid similar to that of solid cables and is paper insulated. However, oil ducts are provided in them. Italic sheath is shown. In the three core oil filter cables shown in figure, the oil ducts are located in the filter spaces. These channels are composed of perforated metal tubing and are the earth potentials. This is the oil channel, this is paper insulation, this is conductor, this is the group sheath. This is oil duct, lead sheath, this is conductor, paper insulations. Gas pressure cable. The voltage required to set up ionization inside the void increases as the pressure is increased. Therefore, if ordinary cable is subjected to a sufficiently high pressure, the ionization can be altogether eliminated. At the same time, the increased pressure produces a radial compression which tends to close any voids. This is the underlying principle of gas pressure cables. Figure shows the section of external pressure cables designed by Hollister, Vogel and Bowden. The construction of the cable is similar to that of an ordinary solid type, except that it is of triangular shape and thickness of lead sheath is 75% that of solid cables. Figure shows the construction detail of a single core conductor channel oil filled cable. Oil channel is formed at the center by standing the conductor wire around the hollow cylindrical steel spiral tape. The oil under pressure is supplied to the channel by means of external reservoir. The triangular section reduces the weight and gives low thermal resistance, but the main reason for triangular shape is that the lead sheath acts as a pressure membrane. The lead sheath is protected by a thin metal tape. The cable is laid in a gas-tight steel pipe. The pipe is filled with dry nitrogen gas at 12 to 15 atmospheres. The gas pressure produces a radial compression and closes the voids that may have formed between the layers of paper insulations. Such cables can carry more load currents and operate at higher voltages than normal cables. Moreover, the maintenance cost is small and the nitrogen gas helps in quenching any flame. However, it has disadvantage that overall cost is very high. Dielectric stress in the cables. So this one is the cable having diameter d and this one is radius d by 2. This internal diameter is small d by 2 and this one is g. This is the g minimum and this one is g maximums. This is the x. Under operating conditions, the insulation of a cable is subjected to electrostatic process. This is known as dielectric stress. The dielectric stress at any point in a cable is in the fact potential gradient At that point, consider the single core cable with a core diameter d and internal sheath diameter capital D. As proved in Art 8, the electric intensity at point x meters from the center of the cable. Ex is equal to Q by 2 pi epsilon epsilon x volt per meter. By definition, electric intensity is equal to potential gradient. Therefore, potential gradient G at a point x meter from the center of the cable is, as proved, potential difference between the conductor sheath is this much value, G is equal to Gx, and G is equal to Q by 2 pi eV volt per meter. Q is equal to Q by 2 pi epsilon 0 epsilon r log by c d by d. Q is equal to 2 pi epsilon 0 epsilon r V by log by c d by d. Substituting the value of Q from expression 2 in the expression 1, we get G is equal to 2 pi epsilon 0 epsilon r into V divided by epsilon E d by d, whole divided by 2 pi 0 epsilon 0 into x. That is V by x log by c d by d volt per meter. Make them equation number 3. It is clear from the expression 3 that potential gradient varies inversely as the distance. Therefore, potential gradient will be maximum when x is minimum. That is when x is equal to d by 2 or at the surface of the conductor. On the other hand, the potential gradient will be minimum as x is equal to d by 2. Or at sheath surface, maximum potential gradient is G max is equal to 2V by d log by c d by d. Putting x equal to d by 2 from expression 3. Minimum potential gradient is G minimum is equal to 2V by capital D log by c d by d volt per meter. Putting x equal to d by 2. G max as G1 is equal to 2V by d log by c d by 2V divided by d log by c d by d, that is equal to d by d. The variation of stress in the dielectric is shown in figure. It is clear that dielectric stress is maximum at the conductor surface and its value goes on decreasing as we move away from the conductor. It may be noted that maximum stresses is an important consideration in the design of the cable. For instance, if the cable is to be operated at such a voltage that maximum stress is 5 kV per mm, then insulation used must have a dielectric strength of at least 5 kV per mm. Otherwise, the breakdown of the cable will becomes inevitable.